It is election season, and there's a runoff between candidate A versus candidate B. And we are pollsters, and we're interested in figuring out, well, what's the likelihood that candidate A wins this election? Well, ideally, we would go to the entire population of likely voters right over here. Let's say there's 100,000 likely voters, and we would ask every one of them, who do you support? And from that, we would be able to get the population proportion, which would be, this is the proportion that support candidate A. But it might not be realistic. In fact, it definitely will not be realistic to ask all 100,000 people. So instead, we do the thing that we tend to do in statistics is that we sample this population and we calculate a statistic from that sample in order to estimate this parameter. So let's say we take a sample right over here. So this sample size, let's say n equals 100. And we calculate the sample proportion that support candidate A. So out of the 100, let's say that 54 say that they're going to support candidate A. So the sample proportion here is 0.54. And just to appreciate that we're not always going to get 0.54, there could have been a situation where we sampled a different 100 and we would have maybe gotten a different sample proportion. Maybe in that one we got 0.58. And we already have the tools in statistics to think about the distribution of the possible sample proportions we could get. We've talked about it when we thought about sampling distributions. So you could have the sampling distribution of the sample proportions, and this distribution is going to be specific to what our sample size is. For n is equal to 100. And so we can describe the possible sample proportions we could get and their likelihoods with this sampling distribution. So let me do that. So it would look something like this. Because our sample size is so much smaller than the population, it's way less than 10%, we can assume that each person we're asking that it's approximately independent. Also, if we make the assumption that the true proportion isn't too close to 0 or not too close to 1, then we can say that, well, look, this sampling distribution is roughly going to be normal. So we'll have a normal, this kind of bell curve shape. And we know a lot about the sampling distribution of the sample proportions. We know already, for example, and if this is foreign to you, I encourage you to watch the videos on this on Khan Academy, that the mean of this sampling distribution is going to be the actual population proportion. And we also know what the standard deviation of this is going to be. So maybe that's 1 standard deviation, this is 2 standard deviations, that's 3 standard deviations. Above the mean, that's 1 standard deviation, 2 standard deviations, 3 standard deviations below the mean. So this distance, let me do this in a different color, this standard deviation right over here, which we denote as the standard deviation of the sample proportions for this sampling distribution. This is, we've already seen the formula there. It's the square root of p times 1 minus p, where p is once again our population proportion, divided by our sample size. That's why it's specific for n equals 100 here. And so in this first scenario, and let's just focus on this one right over here, when we took a sample size of n equals 100 and we got the sample proportion of 0.54, we could have gotten all sorts of outcomes here. Maybe 0.54 is right over here. Maybe 0.54 is right over here. And the reason why I have this uncertainty is we actually don't know what the real population parameter is, what the real population proportion is. But let me ask you maybe a slightly easier question. What is the probability that our sample proportion of 0.54 is within 2 times 2 standard deviations of p? Pause the video and think about that. Well, that's just saying, look, if I'm going to take a sample and calculate the sample proportion right over here, what's the probability that I'm within 2 standard deviations of the mean? Well, that's essentially going to be this area right over here. And we know from studying normal curves that approximately 95% of the area is within 2 standard deviations. So this is approximately 95%. 95% of the time that I take a sample size of 100 and I calculate this sample proportion, 95% of the time I'm going to be within 2 standard deviations. But if you take this statement, you can actually construct another statement that starts to feel a little bit more, I guess we could say, inferential. We could say there is a 95% probability that the population proportion, P, is within 2 standard deviations of P hat, which is equal to 0.54. Pause this video. Appreciate that these two are equivalent statements. If there's a 95% chance that our sample proportion is within 2 standard deviations of the true proportion, well, that's equivalent to saying that there's a 95% chance that our true proportion is within 2 standard deviations of our sample proportion. And this is really, really interesting because if we were able to figure out what this value is, well, then we would be able to create what you could call a confidence interval. Now, you immediately might be seeing a problem here. In order to calculate this, our standard deviation of this distribution, we have to know our population parameter. So pause this video and think about what we would do instead. If we don't know what P is here, if we don't know our population proportion, do we have something that we could use as an estimate for our population proportion? Well, yes, we calculated P hat already. We calculated our sample proportion. And so a new statistic that we could define is the standard error. The standard error of our sample proportions, and we can define that as being equal to, since we don't know the population proportion, we're going to use a sample proportion. P hat times 1 minus P hat, all of that over n. In this case, of course, n is 100. We do know that. And it actually turns out, I'm not going to prove it in this video, that this actually is an unbiased estimator for this right over here. So this is going to be equal to 0.54 times 1 minus 0.54, so it's 0.46, all of that over 100. So we have the square root of 0.54 times 0.46 divided by 100, close my parentheses, enter. So if we're around to the nearest hundredth, it's going to be, actually even around to the nearest thousandth, it's going to be approximately 5 hundredths. So this is going to be, this is approximately 0.05. So another way to say all of these things is, instead, we don't know exactly this, but now we have an estimate for it. So we can now say we are confident, so we are confident there is a 95% probability that our true parameter that we're trying to figure out, that we really want to know the answer to, is within 2 times the standard error, 2 times the standard error of our sample proportion that we got. And what's 2 times the standard error? Well, this right over here is equal to, our standard error is 0.05. So 2 times that is 0.1. And so this is kind of neat. We can now say, confident, there is a 95% probability that our true parameter is within, or let me say it this way, is in the interval, from, so if we are 1/10 below our measured sample proportion, so that would be 0.44 to 2, and if we add 0.1, so if we go 2 standard errors above this, we would get to 0.64. And this is pretty cool, because what we have just established, this right over here, this interval right over here, pollsters will actually call this a confidence interval. Confidence interval. And our level of confidence for this confidence interval is 95%. In the future, we might tweak this probability, but 95% is what people typically use. So that is our confidence level. And now a related idea that you'll often hear is this notion of a margin of error. Margin of error. And you could view that as half of the length of this confidence interval, or the radius of the confidence interval, some people might say. If the interval itself is from 0.54 minus 2 times our standard error, 0.1, to 0.54 plus 2 times our standard error, which is 0.1, then in this case, 0.1, 2 times our standard error, the thing that we are going above and below our actual estimate, that is our margin of error. So our margin of error in this circumstance is 0.1. And so you will actually see this reported in newspapers. You'll say such and such pollsters, they actually did a poll, they sampled 100 people, they got 54% of those people said that they would vote for candidate A, and there is a 10% margin of error in this scenario. And you might be saying, well, how could we reduce that margin of error? Well, if you want to reduce the margin of error, you want to reduce this right over here. And what's the best way to reduce this? Well, increase the denominator here. And so what you will generally see is the larger your sample size, a smaller margin of error you'll have, or a tighter confidence interval you'll have.